Sparse matrix is the one which contains very less number of meaningful elements. Most of the elements are zeros. Only very less number of elements will be having values other than zeros. Normally, the number of meaningful elements are at most 1% of the total number of elements of the matrix. Then it is called as a sparse matrix. In order to conserve the memory requirements, we propose here a representation such that memory requirements to store the sparse matrix information will be reduced. The main theme is as follows. We store the size of the matrix, number of rows, columns, and number of meaningful elements in one row. And then subsequent rows will store row and column indexes of the meaningful elements of the original matrix along with the element values. Thus, the memory requirements will be reduced. That is, for any element, we store row and column index and its value in one row. Thus, we require 3 locations to store any element information. If there are n elements, then we require 3n locations plus 3 more locations are required to store the original matrix rows, columns, and total number of elements, meaningful elements. Thus, totally with 3n plus 3 memory locations, we can store the sparse matrix elements information. It is possible that once we have this one, if we require, the matrix can be generated from this representation. That is, this is a reversible transformation. First, row and column indexes of the original matrix, that is 10, 10, are stored in the first row. The original matrix is traversed element by element, and whenever we find element which is other than 0, its row index and column index will be stored along with its value. Now, we found that in the first row, that is 0th row, and column 1, a meaningful element 2 is found. Thus, its row index and column index will be stored in the resultant matrix. Again, we found another meaningful element at row 2, column 3. Its value is 1. Thus, its row index, column index, and value is stored in the resultant matrix. Again, we may find another meaningful element at column 7 of the same row 2. Thus, its row index and column index will be stored in the resultant matrix. Again, we will find another meaningful element in row 7, column 3. Its value is 2. Thus, its row index is 7, column index 3, and value 2 is stored in the resultant matrix. By now, the source matrix A is traversed completely row by row, element by element, and each of the meaningful element information, that is, its row index and column index, is stored in the resultant matrix. Now, how many meaningful elements we could find in the source matrix? 4. So that 4 will be stored in the first row, second column of the resultant matrix. Like this, the resultant matrix, which we call as a source sparse matrix representation of the original matrix, is created. That is, in the first row, original matrix row size information along with the number of meaningful elements in the original matrix, and the subsequent rows contains row and column indexes along with the values of the meaningful elements of the source matrix. Thus, the amount of memory required for the resultant matrix will be comparatively less than the original matrix. It is possible that once this matrix is given any time, if you wanted, source matrix can be generated as the location information of the meaningful elements are available in the resultant matrix. Thus, this is a reversible transformation.